All right, let's get started. I hope everyone have recharged, and let's train our brain in a reverse way. Back propagation is one important feature of modern neural networks, so we have to flip the coin back and forth again. This session, we'll be talking about AI for power. How do we leverage the new intelligence that were enabled by human-engineered machines to advance the energy sector? And we have a wonderful panel together, including Dr. Tassos Golnas, who is a program manager at DOE, and he oversees overarching the overall landscape of DOE and how do their vision. He'll be talking about the DOE's vision about artificial intelligence and energy. And then we will have Dr. Lina from Harvard University, who is a control and optimization expert, and she applied machine learning to many sectors, including power systems, building systems, transportation, and so on. And then we'll go with Dr. Chris Wright, who is the president of NEC Labs, which is about 4 miles from Princeton. And they basically engineer all kinds of digital systems, all the way from sensors to edge computing to all kinds of intelligences into energy infrastructures. And finally, with my colleague, Professor Egemen Kolemen, who is associate professor of mechanical engineering, and his lab does all kinds of very interesting research on fusion. And one of the recent breakthroughs his lab made is how do we control the sophisticated plasma systems for future fusion systems. So with this, I would like to welcome Dr. Tassos Golnas to share about his opinion and what DOE is doing regarding artificial intelligence.
All right, how about that? Well, again, I want to thank the Andlinger Center for the invitation, and I hope to give you guys an overview of what we're doing at DOE with respect to AI. It will not be exhaustive, so don't hate me if you know something that I'm not mentioning. So that's the topic, and I just want to start by showing you essentially the continuum of research, development, demonstration, and deployment, and how this continuum is served by various offices at DOE. You can see Office of Science, right, working all the way to the very low TRL, and then ARPA-E is straddling research and development. The Office of Clean Energy Demonstration, obviously, is responsible for technology that is at the level of ready to be demonstrated in the field, and then the Loan Programs Office takes care of deployment. I come from the applied offices, right, from the Office of Energy Efficiency and Renewable Energy, and we spend quite a bit of the space here between early stage R&D, sometimes all the way to deployment. What I didn't mention is, I think it's quite useful to see what's our primary purpose by funding R&D, right? I mean, it's essentially to reduce risk, right? To de-risk technologies at various levels of development. This is, I don't need you to read all the details here, but this is an overview of what my parent office, the Office of Energy Efficiency and Renewable Energy, has done in the last 10 years, most of it in the last 5 years, I want to say, subjects of research that are AI-enabled, right? And they start all the way from what you want to say, maybe simpler problems of detection and classification, and they go all the way to forecasting, materials discovery, things like optimization, control, and recently, with the advent of large language models, insight extraction from structured and unstructured text data. These are, I think, 2 quite useful reports, if I may say so. They both have the same name, so it's going to be a little confusing. So I have added the links at the bottom. The first report on the left, that was done by DOE under the auspices of the executive order for AI that came out last year. And it focuses on the modern grid and how AI can enable this modern decarbonized grid of the near future. The second one was written by the national labs, and it tackles 5 problems beyond the power grid, right? So that, as well as energy storage, energy materials, nuclear energy, and carbon management. This was published last April as well. So I welcome you to take a look at them at your free time. Which is, this latest report is a great segue for this slide. And what I'm going to talk about now is FAST, which is one of the best backronyms I think we have come up at DOE. Right? It's Frontiers in Artificial Intelligence for Science, Security, and Technology. And we have essentially these goals here, right? 3 of them are already the mainstays of DOE's mission, right? It's security, science, and energy technology. But we're also trying to build a talented workforce around AI, as well as develop the necessary expertise for AI governance. What is FAST about, right? Again, you don't need to read all the details here, but the concept, and this is a proposal to Congress right now, right? So it's not a funded project yet. The concept runs around 4 pillars: data, compute, models, and applications. The data is AI-ready data, right? I mean, the fuel of machine learning and AI. The compute, as well as the models, they need to be at the frontier scale because they need to address the problems that are, quite basic and quite complex. And finally, the applications are in areas that are strategic and critical for the security of this nation. Now that you know about FAST, we'd like to know what you think about it, right? So as we're contemplating how to build this most powerful AI system that is built for the public good, we'd like to hear the public, what opinions it has about that and the way to build it. So take your phones and take that picture of the QR code. This will take you to a public input, right? It's a request for information, an RFI, and there you'll see 6 questions around these topics. Right? Please take some time and give us your answers. There's already a lot of participation. I've heard that we probably crossed 1,000 answers. So do take some time and make yourself heard through that vehicle. And again, don't forget that you have until a couple of Mondays from now to give out the responses. That's it.
Hello. I think we were trying to be nice to our visitors. You can always see me here. Stop by my office whenever you want. But that's why I was going to go last, but it doesn't matter. So I'll talk about AI for fusion. It's a very exciting area. AI has a lot of hype going on, and fusion has a lot of hype. And AI for fusion is double hype, hyper-exponential growth. Okay, so what is fusion? Fusion is the main source of the universe. And here's a good fusion reactor. We love it. We use it all the time. That's how we exist. It's a bit big for our purposes. If you want to run a cluster of computers, this is a bit big. Maybe you can use a Dyson sphere or something like that, but maybe in 1,000 years. So what we try to do is put the sun in a box. And this is the box. Well, you need to compress this thing. So we can't use gravity. We use magnetic fields. So basically, literally, we take the sun and put it into 2. This is a Houdini trick. We took 1 sun and split it into 2. Now, what we're doing is it's like a donut. So this is a cross-section. You see the cross-section. And we kind of elongate it because it makes better fusion. So, but basically, that's it. You put the sun in here. And I'll talk about how we can use AI to make the operation of a fusion reactor better. So what is operation of a fusion reactor? We have some desired outputs. what do we want? We want a lot of energy. We don't want any disruptions. We want it to continuously produce electricity. And then we have a controller, that's our hammer. We have the plant, that's the fusion reactor. We have some diagnostics. And hopefully, our outputs are equal to our inputs. So basically, we just get the power that we want without any trouble. So first, I'll talk about how we can do better measurement with AI. So what is measurement? So we have a plasma state, the temperature of the plasma, let's say. We call that usually X. This is X. And then we have some measurement, Y. Maybe that's the photon counts on your camera. So this is a map from the temperature to your camera. And basically, we're trying to find this inverse of this map. Given the camera images, how can I find the temperature, right? So how can AI help with that? First, this is the sun again. This is the core of the sun. This is the edge of the sun. We usually look at temperature from the core to the edge. Core is hotter than the edge. This is like 100 million degrees or so. So this is what I'm going to use, like core, edge, and parameter of interest. So we get, this is a fusion reactor. We have a lot of diagnostics and analysis going on, and inputs of your diagnostics, and out comes your reconstruction of what the plasma looks like. So we have some codes that can do this, but what AI allows us to do is map all these measurements, xi, to the profiles, like what the temperature and so forth is in the plasma. But you can do this, and you can just take this code and do a surrogate model. A lot of you probably heard of what a surrogate model is. It's simple enough. But what extra you can do is this. These diagnostics always fail. You're in a nuclear environment. There's nuclear damage. The noise goes up. Some of them fail. When other things can happen. So what this allows us to do is we can drop one of these measurements, for example, and try to reproduce the profiles, the temperature we want. And we can add noise here and then try to reproduce. By doing this change of the XI, the sensors, and mapping it to YI, we can design a measurement system that's robust to any diagnostic failure. So think about it. You have hundreds of diagnostics. Any one of them can fail. Any two of them can fail. So you can do all the permutation. And if you try to write a code that thinks about all possible failure modes and fixes that, that's really, really hard, maybe impossible. But AI can allow us to do it just by feeding the trouble that we want, and the solution comes out from AI. All right, here's an example. We turned the system first time in the fusion reactor. This is the temperature measurement we're getting. Temperature is not constant. Just basically diagnostic failed the first time. Someone was jamming the door of the cable, really. So you get nothing, but the temperature profiles are shown here. So basically, it can infer from other diagnostics that this diagnostic failed, I should make up for it. And this is all being done automatically. If I were to write an if-then code, that would take years. Another thing you can do is the plant process. So fusion is extremely hard to model. There's quantum things going on, lots of things going on. So how do I model this? When I say model, I'm talking about, like I said, this is my state, and I have a control U, and I want to find my future state. So what is the future plant going to do in an hour, for example? And that's the map F, and I'm trying to find this map F. So it allows AI is going to help me with this finding this. So here's what you get when you take all the data and make a model out of this data. So here's the control input, the power input that I'm putting, the heating. And this is what the fusion is doing in time. So the rotation is going up, density is going up. And I'm playing this through. This is all data-based. No fundamental physics code. And I can replay shots and make new discharges and optimize for it. OK. Another thing, finally, what we want all these things for is control. Because if I'm not going to use the data I have, information I have, what is the point? So for control, the idea is that, again, I have this map here. I have the control and the state, and I want to find a future state, right? This time, I want to find the best control that gives me the state that I want. I want more power, no instability. OK, how do I find this U? There's lots of methods, but one example is reinforcement learning. This is alpha star. So basically, you give the game to an AI system, and it just plays pushing randomly the buttons, and then at some point, it learns how to play the game just by playing by itself. Here, we use similar ideas to train control systems for fusion reactors. And the idea is shown here. So here's some actuators. Let's say I'm putting more power in. There's a stability limit. If I hit that, the black one, I have this disruption, so I get some sort of a plasma just dies off. So I want to avoid that, and they kind of need to go through this actuator phases. And the idea is that you have to kind of thread the needle, go above to get to the highest possible fusion rate without instabilities. So we did, to do that, we have all these diagnostics here and all these controllers. And in the middle, you put this RL system. And it's only using experimental data. It's not using anything else. And it's able to find, if I can play the video, I hope it plays. So this is the real, this is the fusion energy gain versus time. So you want this to be high. So it's going high, but it sees the red thing here is instability. So it says, oh, it's unstable here. So I kind of need to stay down. And it kind of finds its way around and gets to highest possible energy production without instabilities. That is a real experiment. Without further ado, I'll let it go. So yeah, AI has a lot of applications in data and in measurements and control. Thank you very much.
Thank you everyone for coming. It's great to follow previous talk and continue talking about control. And now I'm going to talk about control for a power grid. So my group have been working on smart grid. There's echo, I will stay here. So for the power system, we have had a lot of nice discussion this morning, talking how the power system can help in the AI. Now let's look at the AI, the power system itself. So I've been changing. First of all, even if we don't do anything, the power system is the kind of largest scale network that human have been made, connecting all the components together. So we have a lot of renewable energy generation, and for those who had those data, you will know like this has a very noisy and has a lot of uncertainty about the generation. So there's also other change. We talk about the data center, and we talk about there's also electrical vehicles, there's a deep electrification. So there's all the changes happening in the grid, and there's also additional very difficult component is the human in the loop. And we have a different type of humans. The big power component of the grid also has the small users. So putting all of them together, the challenges, like why people think about doing the AI for the power system. So all those things together, first we had the volatility. There's no guarantee about the renewable energy generation for the next, even the second. We have complex system, we have uncertainty from every component. So like there's one challenge. Like I had a model-based control background during the training. When I was trying to work on those problems, always one difficult component is they are very difficult to model. Like what's a model to start with? And now let's look at the opportunities in power system, what have been going on. So we had a lot more and more smart devices which can do the sensing, like similar to the fusion one. We need the sensing being improved. And we also have like smart devices from the residential also to the commercial. And we have upgraded communications infrastructure, can connect all the components together. We have the AI supercomputing that's available. When we're putting them together, opportunities is we have the better sensing, we have better computation, we have better data analysis tool, we have the better communication, can put in data together. That's kind of motivated like to do the AI for power system. So this launch, I heard a very interesting conversation, like what's really the AI? And I don't think there's a formal definition what is AI. So to talk, I will kind of continue talking about control, reinforcement learning. So give a very quick introduction of the reinforcement learning. We actually had a survey paper which goes through the recent progress by using the reinforcement learning for power system. What's really the current progress, the other ones, and the future challenges. So I will give a very quick introduction. So what's reinforcement learning? Continue the previous talk. Like the reinforcement learning, typically, we have an environment, either the fusion system, power system. We have the smart AI agent. We try to make a policy. The policy is we had the sensing, we observing how good the system is running. Based on the sensing, taking the control action, like something we can do. So how are we going to find this policy? So now with AI technologies, we can parameterize this one by a deep neural network. And how are we going to update? By, again, observing how good the system is running. Like that's kind of, you can define the reward, you can define as a cost. And this is one of the advantages that like AI being used by so many different communities. The reason I would say it's very easy to use. Even without the methodologies, I kind of putting this as a black box. Just keep training the control policy, by using the data to improving, finding the optimal policy for long-term goals that you want to achieve. So with this agenda, like we see a lot of exciting news, including the ChatGPT. Like look at the last layer, it still go ahead to using the reinforcement learning to the fine-tune. So one challenge, or like look at how we're going to use this kind of AI for power system. Like, can we bring the success from the simulator data center just computing system to a physical system? So what do I mean by that? But first, let's look at why we even starting thinking about doing those kind of model-free, data-driven reinforcement learning method. Because as I mentioned, we have a lot of model uncertainty. So like, first of all, it actually fit into this framework very nicely. So we had observation like from power engineer, we have a lot of sensors, we have a lot of physical variables. You can put in those as a state. And the control policy going to learn from the AI algorithm, the action, depending what kind of smart devices or even not smart devices, you still have the control action you can take for the building, for the classical power component. So now why we actually get even thinking about doing the model free, first, I said the system getting more and more complex. It's getting bigger, many things getting connected, more human, active human in the loop. So here, if I just go ahead to try some method, not going to worry about the model to see the outcome. Like first, it's very easy to use, has a lot of model uncertainty. And secondly, is when we really implement the learning algorithm, rather than just using the control policy we learned in the end, we can just keep updating, using the data. Now you got the new data, situation getting changed, I got new data, use the new data to update my policy. So that's the hope to adapt to the sudden change of the system quicker. And last one, I would say we can have a discussion later during the discussion, like this actually will be, like some people will argue it's hard to use, you fit in the framework. On the other hand, in my opinion, depending what's the unknown component, I can figure out a way to just put in my learning algorithm, work with the classical control algorithm we have been doing. So about what the challenges? So first of all, we really care about safety. Like we're doing the AI, so the theoretical proof, can we guarantee it's always being safe? Is the control policy safe? We train the policy using simulator. Simulator not going to be the exact truth. How are we going to close the sim-to-real gap? Is it going to be robust to the measurement noise or not? So there's some potential solution like we propose in the paper. Feel free to read. And the other bigger challenge, scalability. So now we actually really want the control action that every power plant, smart devices can take once they see some local changes happens. And this is very different to send the control command, like sending the information to the data center, wait a few seconds, getting a solution. And this, I talk about communications, like we have more communication. If you look at the communication delay, it's still not able to catch up with what we really need. So again, we have some proposed solution, how we're going to do the decentralized structure, what's really the structure we should build for the communication. And the last one, like the data. We mentioned the data in the morning. I would like to say for the power system, if we really want to use the AI to improve the power system operation, for you look at winter storm, heat wave, or the future when we have a deep electrification, we actually have very limited data. But do we really have a very good success how our power grid to survive during the winter storm? We actually don't have much data to start with. So that's actually pose a question. We cannot just doing the black box following the existing data to train it. So we need using other methods combined with AI technologies to improving the performance. So in the end, just like one half minute, we also recently look into the large language model, how the generative AI can be used in the power system. We actually dive into 7 concrete cases. Although like for the people who actually form power system operator, you will see these are the cases that everyone actually need to deal with. We had a report, right, which cases the current AI doing well, which is not doing well. So given the interest of time, I will leave all the things for the discussion. Thank you.
Is this working? Oh, great. So thank you for the invitation to come. I really enjoy speaking these. As was mentioned, we're just down the road. So anybody who's interested in collaboration, I'm really interested in that from our side. So first I wanted to talk a little bit about NEC. And I'm going to use this for a couple different pieces. One, most people don't really know what NEC is. They remember that there used to be a projector in their room or a TV or something like that. That was NEC. And they were really strong in networking. They were really strong in supercomputing. As the telco bubble burst, They contracted from being a worldwide company to being more of a Japanese company. But even so, they actually still cover a wide range of different areas, from submarine cable systems to terrestrial networks to digital finance, digital government. We're building targeted cancer design, so digital medicine. They do retail. They do firefighting and disaster recovery, healthcare, broadcasting, education, across the board. And there's a couple pieces. One, NEC is unique in this way, I think, because there's not a lot of companies that do all of this. But two, I will tell you that all of these customers are asking for energy efficient solutions. So it is not just a single problem. It is not an AI problem. Every one of these industries is growing at a rate that is unsustainable, and they all need to figure out how to fix that. So that's one. Two, every one of these industries wants to use AI because they're convinced that it's going to save them factors of 100 or factors of 1,000. I'm not sure if it's going to be there, but NEC is certainly selling lots of stuff into this space. The last thing I will mention that I think was very, very, very Japanese of NEC, that they actually invested in machine learning, in deep learning 15 years ago. And that means that we're deploying real applications that have real value in these markets right now. Again, many of you may not know NEC, but NEC knows you. Because if you've actually gone to any event where it was ticketless, right? Madison Square Garden, where you're walking through. If you were flying ticketless, if you were being inspected by CBP, it likely was an NEC system. So those are NEC AI systems that are at the root. So I also mentioned that the other piece that I, again, love from the NEC perspective is that we are, NEC Labs America, we're an industrial lab in the same venue as Bell Labs. I spent 23 years in Bell Labs. The person who started NEC Labs came from Bell Labs. Of the 7 presidents, 4 of them have been there. So we are really a lab that actually keeps one foot in industry, because we are coupled to a parent company like NEC where we can interact with customers and we can understand real customer problems, but we also keep one foot firmly in academia, right? So we publish as many papers as we actually transfer assets into NEC. We also broadly collaborate. We have 40 or 50 interns every year. We have direct interactions with universities. We have contracts into the US government. So it really, from my perspective, is the ideal place to be, because good research requires understanding good problems, and that really is the coupling that we actually try to do. So I wanted to tell you a little bit about the problems that we have in this space, because I think it directly maps to this idea of how we can use AI not just for power, but really there's a sort of a model for all industries. All the customer solutions we're building look the same, and I think there's some interesting things to think about. So one of the challenges we have is we are being asked to solve problems of increasing complexity. One of the easiest way to solve a complex problem is to break it down into subunits, right? That we can actually decompose a complex problem into simpler problems and then put them together. But more and more, we're finding that there is coupling between problem areas, coupling between industries, and a lot of the effort that we put in is those coupling terms of higher order, which are not easy to get if you've actually made the approximation that all the degrees of freedom are separable. So increasing complexity, increasing scale. There's a sort of naive way of looking at this and saying, oh, we have to do it for 1 billion people. But the reality is the 1 billion people all want a custom solution for their own. So we have to actually deploy these kinds of systems in a way that is dynamic and changes at this sort of global scale. And the last one is we have to do it in limited resources. And there's a piece that, again, comes back to this coupling, which is that we're pretty good at solving point solutions. A company comes to us and says, can you solve this? We can solve that. The second that it actually requires collaboration between companies, right? So instead of a local metric of optimization, we have a global metric of optimization. That's where we really are right now. So collaborative problem solving is one of the key things that I see as a challenge globally, but it specifically lands in this power situation as well. Because if every company or every person optimizes for their own personal power, that means that we are losing that cross-coupling. We're losing the ability to have interactions between industries balance and have a global minimum that is lower when those two industries work together than you would get if they were actually independent. And I wanted to mention this, again, is something that we do all the time. This idea of efficiency, I think it was mentioned a little earlier this morning. The unfortunate thing is energy use is not going down, right? No one here should have this thought that, oh, it's going to plateau and come down. We are training a generation that expects that the world is going to adapt and automatically work to them, that they have instant access to information, and there's a cost to that, and that's going to be going up. So how we manage that going up, that's a broader thing of how we deal with the demand, but we shouldn't have any waste. We need to drive for the most efficient systems possible. And that means we can no longer design these systems where we sort of say, okay, I'm going to design with some extra capacity, and as long as I'm inside of that range, the system doesn't fail. I need to make sure that my supply and demand are matched. And that means the time scale over which I'm making changes to the system. It means the understanding of the system has to be really, really fine-grained and careful. And that's what we're going for. It's not fusion. I will mention, I just want to, just a personal thing. I think when I was like 13, I came to visit the plasma physics lab here. And so there's probably some connectivity of me being a lab leader now to that visit. But that kind of work is, I think, critical to understanding and making these work. How do you match supply and demand? How do you do that fine-grained control to actually optimize things? And how do we do it? We sort of look at all of our problems in this idea of sensing the world. We then perceive, understand, and predict in the digital space, and then we take an action. And if you think about it, all the power problems that we have, all the real customer challenges are like this, right? We can sense, we can measure, we know how to take action, but the AI systems that allow us to do perception, understand the features in complex data, understand that by associating it with a meaning, and taking a prediction, that's the key value. So I'm going to end here because I just hit 0, but this global context of how you actually get policy from government, how you actually get demand from industry, and how you do that automatic negotiation on a time scale, which is sort of automatic and microsecond or second, rather than weeks or days or months or years, is really what we see driving cost reduction in global supply chain and industry, but also cost is related to power, and we can use that same kind of technology to optimize power overall. Okay, thank you.
Thanks, Chris. Yeah, so we have heard a lot of great insights through the panel presentations, and I'm going to throw like 4 questions, very short questions. And we know AI for power is one way of applying artificial intelligence. And whenever we talk about applied AI, we ask 4 questions. One is data, compute, algorithm, and application. So I'm going to ask each of you to address one of these aspects within a few sentences. So Tassos, my question for you is about 10 years ago, I was involved in the future of the grid study at MIT. And one of the conclusions we have is that whenever you want to do anything related to energy system, you need a lot of data. And the data sometimes the priority is confidential, it's not open to public. You can't allow everyone to know where is the critical infrastructure of the grid. And I guess for transportation systems or other energy systems, very similar. My question to you will be, what's DOE's perspective on how do we manage data and make sure the data is available for innovation from the public and at the same time ensure the safety side of it?
That's a great point, Minjie, and it is a problem, right? There are 3 problems with data, right? I mean, there's scarcity, there's inaccessibility, and low quality, right? So all of them can be detrimental to one degree or another to machine learning. There are obviously multiple ways to address that, and what the government can do is find solutions that are acceptable to the stakeholders that have the data and maybe they're reticent in sharing it for probably very valid reasons. Right? And I think one of the technologies that is providing some hope there is these federated learning, but that happens under privacy-preserving conditions. Right? So there's active research on that front. DOE, the Office of Science, and specifically the Office of Advanced Scientific Computing Research, put out a funding opportunity a few months ago with exactly, one of the topic areas was exactly that, right? So we're very eager to see what the researchers can do on that front. We think in the utility space, in the transportation space, there's going to be tremendous application if this, is scalable. From that, point on, there are a lot of other things that, the government can do. It can definitely help with, measuring new data, right? So it can fund essentially measurement campaigns. It can buy and liberate data, and we did that in the solar office. We had a solar data bounty prize, where we gave a bounty to whoever wanted to share performance data from the power plants, so that the R&D community can access them and build new models, evaluate old models, things like that. So there's a lot that can be done, right, to ameliorate the situation.
Yeah, how active is DOE looking into this? Is like on top of the daily schedule, or is it like coming up and down, this kind of concern?
It really, it's absolutely, front and center, and obviously every team has different ways to address that because they have different stakeholders, right? It's a different thing to have the nuclear reactors as your customers, different thing to have, like some scientific enterprise, and a different thing to have, utility and transportation companies, kind of wanting to sharing the data, but being too scared because they're gonna, these are maybe privacy carrying informations or sometimes commercially sensitive information.
Right. Great. Now we'll move on to compute. Also the compute question to Egi. So, fusion systems are very complicated, and you have to model all kinds of things. Do you feel like the existing computing infrastructure and GPUs are fast enough, or it will never be fast, or will always come up complicated questions that overdriving that the GPUs cannot handle? So how do you look into the race, or is it sufficient, or is it not? How would you read into this?
I see some more confused friends here. They enough compute. They want more compute. Well, it depends what you're looking at. I think for a lot of practical applications for diagnostic analysis and control and optimization type things, I don't think we need that much compute if you're looking at small wins here and there. But if you're looking at fundamental discoveries, like, I'm loud enough, I suppose. If you're looking at fundamental discoveries at the quantum level or some deep understanding, that requires you to run these very large compute systems. And there, I think people think that we can use more compute. But I'm a bit on the fence on this. It's always easy to say we want more compute. Right? It's an easy thing to say, but I think we have to be very careful on deciding where we do really need the compute versus where we don't. I would say for vast majority of applications, we don't need that much compute. We do, but the current levels are, fine. Yeah, I don't know.
Yeah, I see. So I guess it really depends on what kind of question you are trying to address. Some of the problems, existing computing is enough.
Yeah, a lot of what I do, for example, let me try to give an example. We try to do real-time compute. So there you can't run 100,000 GPUs in a cluster, right? There's a lot of work that's going on for real-time compute with FPGAs and other systems. So there needs to be a lot of work on that front, and I think there is a lot going on there. How to do a lot of compute in a millisecond, microsecond, whatever regime. And I can name some companies, but not worth it. But so I would say a lot of work needs to be done on the AI-specific compute, real-time, fast. And for a lot of applications, I think we do have reasonable amount of compute that we already, I mean, for example, when you look at large language model training sets and how much compute they use, that's huge. It's very unlikely that many of the scientific problems that we're using will need that much. I mean, I think, if one of these large language meta companies go under, there'll be enough GPUs for all of us to use. That's my feeling.
Yeah, I heard from Steve Cowley there was some ongoing discussion between PPPL and NVIDIA. I'll throw out a wild question. Like, if we're going to have a fusion, real Q larger than 1 fusion system, do you think the existing computing infrastructure is enough, or we have to invent new computers to really control the fusion system?
New computer, I would say we probably need to develop new real-time compute systems for work that I know I need to do. In terms of physics calculations and extrapolation, that depends on who you ask, especially if we're trying to design these new reactors that we don't understand that much. Probably yes, but if we're going to build the nth plus 1, a magnetic confinement tokamak, probably we're okay.
Great.
Nate is laughing. He's like, no, we want to.
We'll save the question for later. I'm sure there are a lot of questions you guys are trying to ask. So for algorithms, I asked Lina, you're trying to apply artificial intelligence to all kinds of systems. Do you feel like we have enough algorithms on the software level, or there's always new opportunities to innovate on the algorithm front?
I definitely think there's always new opportunities for the algorithm. Like in the talking for the power system, I said there's challenges like to guarantee the safety, robustness, which is like this issue are not really that important, I think, for the large language model, but which is very critical for the physical system. And how to design algorithm to have the performance. There's a lot of research going on, but on top of it, people actually, for us, we actually want a little bit harder guarantee, right? It's not just with a 90% guarantee. If you say the airplanes only had a 90% of safety, no one going to take it. And that's a similar situation for the power system. We try to work with the power industry. Right? They always, okay, if my system don't have issue right now, I don't want to change much, right? Even I say probably I can improve the guarantee to how much. So there's a lot of still needs of the algorithm design side. And this is the one about scalability, same thing. I think for the kind of connecting with Egemen's question, issue about the fast computing, right, is even when people give me a huge amount of GPU, I wouldn't say this is solve my problem, because think about for this building, if I want to do the real-time adjust, about lighting, about the temperature, it's not putting a GPU on here, there. I really need the edge computing, so I want my algorithm to can work with those smaller devices, but can react very fast. So this is not resolving by those kind of GPU, give me the data center problem. And just putting that out is a need of the computing and the algorithms.
Right. Probably sometimes code design. You have to understand the computing.
Yes, right. The code design with what you need for the large-scale system, and then the algorithm side, and then also the device side, right? Kind of code design of the 3 level, even not just 2 level.
Right. So, a follow-up question is one of the areas where machine learning has really made great advances is image processing and language processing, where there are a lot of researchers looking at these 2 problems because it applies to so many areas. One of the uniqueness of energy type of application, probably I'll throw this question to Chris, is energy applications so segmented, right? There are so many different things you can ask, and there are not enough people. If all of us working on power system, probably we can quickly advance the power system control rapidly. If every one of us work on transportation, then maybe we can make great advance. But yeah, self-driving is one example. So for some of the niche segmented energy application, what is NEC's strategy? Or how do you guys sort of try to figure out in an optimal way?
Yeah, so I think the one thing that I can guarantee is that we're not going to run out of problems. Right? I think that's you can quote me on that one, it's not going to happen. But I think the key, right, and the key from you're running a lab like mine, we don't want to solve specific problems, right? If you're solving specific problems, then you run out of people really quickly. Yeah. But if you understand the sort of general nature of the problem, and you can say, oh, this is a problem that applies in all these different locations, then all of a sudden the number of people you need can actually go way down to actually address those problems. So I think the piece that we need to do is really focus on the problems that we have. And once we focus on the problems, then find the sort of widgets that we can go in to solve those kinds of problems, right? I mean, from our perspective, things like global supply chain, right? We just had a disruption. We spent, I don't know how many years optimizing for just-in-time, low-cost supply chain. And then we had Ukraine, we had COVID. These sort of global things changed the game completely. And we need to re-optimize for stability and for, maybe cost at some level, but quality also starts to come in. So I think that so long as we're doing things, there's going to be a need to optimize those things. And, right? And at some level, if we all close our eyes, every time we say AI, we're talking about optimizing or sort of trying to apply a numerical understanding of a situation to gain a better outcome. And like I said, we have whole hosts of companies that are coming to us and saying, yes, you've created these large language models. It's a great hammer, but I don't know how to use a hammer. Can you actually come in and help us to figure out how these pieces go? So I would say that our biggest challenge from a people perspective is not having more graduate students working on AI. This is sacrilege because I want to hire them, so please do keep training those. But creating students that understand how to look at a new situation, understand a problem, and map it into something that is solvable with AI, with mathematics, with whatever else we have. So I think as long as we look at it that way, we won't run out of problems, we won't run out of people, and we will prioritize the most important problems rather than let them go to the side.
Very important. So think about problems as hierarchically and really ask deeper questions beyond just applications.
Yeah, start at the high level, because if, I know from my history that research is fun. It is great to solve a really hard problem, but the commercial value of that is not necessarily related to how hard the problem was to solve.
Absolutely.
So you have to talk to customers. They're the ones who have the money, they have the energy, they have the real problems. And how you do that mapping, that is a skill that we need to be training.
Great. So we have went through all the 4 topics. I have one last topic, and then we'll open it up for Q&As. So my last question is the uniqueness of energy system like power system or fusion is super important. And safety is number 1. Like, you don't want the power system to fail. You don't want, if there's an AI to control the fusion, like, how will us trust it as public? And how will the government trust it as and ensure somebody is responsible for the safety side of it? So my question to the entire panel is, regarding the application of AI to energy, regarding safety side, how do you think government and academia and industry and research labs should coordinate to make sure while we are advancing the technology and making it better and better, we're also addressing all the challenges around it, like safety and responsibility and transparency, so all these kind of topics. So maybe everyone can say a few sentences about it.
I can start, right? So there's many ways to skin that cat, and that's totally inappropriate, simile here. But you can certainly, and we're doing research towards interpretable and explainable AI, right? So I think this is the holy grail, probably, especially for these scenarios where AI is used in areas where safety is of utmost importance. Nevertheless, even there, I wonder if transportation system operators, the power system operators, if they have a threshold below which the savings are just too good to deny, even at the cost of explainability, right? I mean, that probably remains to be seen. But I think via stakeholder engagement, right, we can come up with the right benchmarks and guardrails, because not every application needs to have the level of explainability and transparency that the safety critical applications do. For the ones that do, it's important to have essentially a set of best practices and ways to validate answers quantify uncertainty, I think that's probably the very minimum. Great.
So I totally one thing I agree. I think the benchmarkers will be very useful. I think the government and also the funding agency can put in more resource for people to discuss. What is better? Okay. So I think, but that's actually the community effort, in my opinion, right? Even if the industry really care, for example, for the power system, there are different level of safety. Like one thing I will see clearly use of the AI to understand the user better, because right now we have more demand response program, electrical vehicles, and those things are new. And even the utility company actually need the data to understand what's really going on, right? This AI can just play a role, it's not going to affecting their classical operation. So, but then for the transmission system level, I think the community effort together will play an important role. But let's really discuss the metric, how much you really want to achieve, and this is some benchmark. First, if you want to do some algorithm, test on this one to look at your metric, and we can talk about for the next level, start with a macrogrid, smaller scale, gradually to expand it. So that's one thing I think for the power system. Another thing, I was always for the safety, if the autonomous driving actually were more critical, we're going to hit a person. So I always think for us, for the most safety critical application, for the engineer operator, we always have some kind of safe operation we can go back. So when people ask me the question, why I do the exploration for my AI algorithm design, how you really ensure the hard safety guarantee? My honest answer will be, you have to probably have some backup plan, and then I will develop in the statistical tool to predict, after 1 second, probably some things I cannot really coming back. Before the bad thing happen, I can go back to my safety operation. But this is need again, collaboration, right? And I can have statistical tool based on AI to understand my system evolution better, and I can find the critical moment when I should switch. Once I switch, if since coming back to the good situation, but can coming back to the AI algorithm to optimize. So that's kind of always my philosophy for the very safety critical application. Yeah, thank you.
Yeah, so I think there's lots of different pieces to this. So one, I completely agree with this, right? You have to have a way to fail. If you don't know what the failure mode is, then you're in trouble. And there's too many systems we're designing without a failure mode. So I think that's one. One piece that I'll add in that, and I'll tell an anecdote, and I won't confirm or deny anything, but a large venue that was using ticketless entry, face recognition, decided that they weren't going to allow any lawyers in who were suing them. Right? Some of you probably saw this New York Times. You can go look it up. So the use of technology, right? There's good uses and bad uses of a hammer, right? So we have to worry about the people as much as the AI. So that's one. The second one is that we have to be very, very careful that we actually are realistic about what AI can do and what it can't do. We are allowing the hype to drive us now, and that means that there are people who, think, oh, AI can make me fly, so they're jumping off of buildings and finding out that doesn't work. We don't have the ability to experiment to find those lines. We need to spend a lot more effort as, all of us, to actually define those lines so that people actually know what they are.
On the safety, I think, I don't think AI is a different type of safety hazard. If you look at there's one, militaristic sort of safety thing you can think of. We all know Sputnik and the exploding phones in Lebanon and so on and so forth. They didn't, this didn't happen with AI, right? If there's a code and if there's a chip, there are ways to make it do stuff without using AI. So AI is just another tool that you can add in to the game. So it's just, I don't think there's fundamentally a different game in that part. But that there's the other part, which is not that safety, like someone, spooked in, but just, will the system fail? There, I think I'm a bit more optimistic than many others. So if you look at why systems fail, my opinion is, for example, if you look at Boeing, airplanes going down, they weren't using AI. They were just using regular PID controls. They just, there was just a complicated system. There's thousands of things going on, and they forgot to connect this one to that one. And if, this fails, this doesn't fail. And when you have, a million PIDs connected, how is it different than an AI system anyway, right? I mean, PID is a control system, just the simplest control system. So I don't think there's that much of a difference in the standard understanding of how that's going to go. So yeah, I think on both sides, both social and the security part and from the military side and the other side, it's just a different tool. We'll just take some time to get used to it. And I feel like when we use AI, my students and I, we become like superhumans in some ways, because things that would take like a decade that I wouldn't even bother doing because it's going to take so much time, now I can say, oh, I can have a grad student do this, right? So it allows us to do things 10 times faster or whatever the X is. And once you have that, no one's going to stop using it. It's very hard to say, well, we're not going to use that system, because at the end of the day, when you look at safety, you can only spend so much money on safety. Planes are going to crash, right? At some point, you have to cut the line. So what AI systems allows you to do is make everything faster so you can be more safer by doing more testing with the same amount of money. So I think what allows us to do is for the same amount of money, we can do better development. So in the generic sense of safety, I don't think we'll be in trouble.
I guess the question is like, how do you... Yeah, I guess the question is, how do you define better performance? Because with all the PID systems, you can sort of prove it, oh, my PID is better than your PID, but now you have all black boxes, and how do you compare?
Well, again, I mean, proof is in the pudding, right? I mean, you have a million PIDs. What you do is you go back and you do crunch testing. No one is writing an equation and showing that failure rate is below 10 to the minus 6. I mean, they're just doing crunch testing, and then you get your solution. And with AI, it's going to be the same thing.
So you have to define the rules.
Yeah, I mean, once you have a very complex system, no human brain can understand it. It's computers that are checking it anyway. I mean, do you think any of these complicated systems are checked by humans line by line?
So you have to set up like rigorous testing scenarios.
Exactly.
So that,
I mean, I'm not saying it's going to happen right away, but the point is that it's not different in my mind than just regular crunch testing that we do for any system.
Maybe there'll be AI checking AIs.
Maybe.
What could possibly go wrong?
All right, I open the floor and for Q&A questions. Any questions?
Yeah. Yeah, hi. I'm Jim Sturm from the Electrical Engineering Department. Is Rob Sokolow still here? Yeah. So I've been a faculty member here for close to 40 years, and before that I designed microprocessors at Intel. And Rob, you were running an energy center, and he came to see me. This is a bit off from the exact topic we were on just now, but it's still very relevant. And you came to ask me, you probably don't remember this, you wanted to know, and PCs were a new thing. We were just starting to get them in our offices. And you were worried about, is the electrical demand, around the country going to go up because we all got PCs, or is it going to go down because the chips get better and consume less power? And I said, they'll consume as much power as they can until we build a fuse. So they're not going to go down. And other people said, well, chips are going to get more efficient. You said, yeah, but there's an infinite number of problems that need solving. When you have these new tools, we're going to use them the exact amount we can. And so the only thing that saved us was laptops, and you had batteries. And the battery could only hold so much, so you had to keep the chip power down. And now here we are again. Infinite set of problems, as you all just described, an infinite set of applications, and you can always do more. And we're talking about energy supply. What's going to sort of set the limit of how much overall AI there's going to be in 5 or 10 years? Is it just going to be as fast as we can build electric power plants? Or is it going to be the people question, that people know what to do with it? Or is it going to be the ability to produce chips? I'd just like to hear some comments. How fast is the whole thing going to go?
I can take a first crack at that. And I think elements of this were mentioned in the previous panel, right? But essentially, energy affordability is a key premise for every administration, right? I mean, that's for every government around the world, right? No government wants the people to essentially starve for energy, right? So that alone, I think, will be enough to keep a cap on some of the use. And then it's going to be essentially a political power, right? I mean, those who, are trying to benefit from it versus everyone else who may indirectly benefit from it, but directly suffers by the unaffordability of power, right? So that's probably that's going to be the control for this process.
If I may, I mean, energy is extremely cheap, right? I mean, if you look at how much energy does a human can produce, by doing with their hands and so forth, and how much per hour you pay a person versus electricity costs. Electricity costs is just cheap, dirt cheap. So as long as we will find use for electricity, more use, we'll use more. I don't see why we don't go orders of magnitude, because it's you're paying cents for taking you from here to shopping mall. I mean, for any type of energy, it's so cheap. The only thing that's stopping us from using more energy, in my mind, is we can't find that great ideas to use it for. And we will find more great use. I mean, there's humanoids. Why not everyone has humanoids or whatever? So once we figure it out, we'll build more. Everyone will want it, and we'll use more electricity. And half the world doesn't have any cars or anything. So I think sky's the limit in terms of energy. It's so cheap. So as long as we find uses, we'll use more of it.
So we have NVIDIA and AMD here, so maybe they can comment on, have they sold out all of their GPUs?
Can I make one comment on this before we switch?
Go ahead.
Just one, because I think it's interesting. So I wonder if in 20 years we're going to think Moore's law wasn't about the amount of compute that we could create, but the demand of compute that people had. And I think if you look at the amount of compute that you as an individual use, it has dramatically increased over that time period. And I see no reason for that to decrease, because at some level you can use compute as a proxy for standard of living, right? That you are offloading things that you would have to do individually to the rest of the world through that compute mechanism. And I think that's the thing that we're going to have, and we're going to have a lot of different proxies. Things are going to be we're going to have a lot of something until it actually asymptotically becomes the limiting reagent. And I think we're going to just sort of move through history, finding that we have different limiting reagents in terms of providing that extra compute that we might be finding in this space. So I think that there's always going to be a demand, because I think that there is a thread through history of the amount of effort that you want to offload to others, and that proxy is compute in the current view of things.
Okay, great. Yeah.
So going back to the topic of how do we trust AI, I have a, quote, full self-driving Tesla, and it's not full self-driving at all. If you let go of the wheel, or if you don't look towards the road, it'll turn itself off. Tell you, stop driving. It'll just, you got to take control. Boom, and gives you actually 5 strikes now. Then every strike to get back, you have to wait a week, because if you violate their policy of using it, that's kind of to me a failure of, it's a hype. That was, you have this huge hype of full self-driving, is not at all, and it's really just assisted driving, which is actually good, because you want AI to stop crashes. That's great, or AI for drug discovery, or AI for some tool to discover things. But it really makes me. I think that it seems to me, how do we get through the hype for AI for, let's say, managing nuclear fusion, which could blow up a large portion of the planet possibly, or something, or let's say nuclear, reactor. If we are really going to trust AI, because if something comes in that it never saw before, like a missile attacks part of the infrastructure, it won't know what's going on, and then if you don't have the operators who understand it in detail anymore, because they're replaced by AI mostly, that could be, the disaster. So how do we prevent that? How do we design for that?
So I can comment on this one, because we're asked all the time, right? You have a customer comes in and says, use AI to solve this problem, and you go, no, we're not going to do that. There's a couple of very easy things. One, never use AI for something that you can't check, right? You want to be able to check, right? So that's why coding is great, writing is great, drug exploration is great because you're going to test that some other way in Citro and everything else. So there's a huge number of applications, but you want to be able to test. Second one, and I think this is maybe not as well thought about. If you look at a company and you have a process that has a team, you have multiple people on the team, you can replace one of those people. You can't replace the whole team, but you can replace one of those people with an AI system. And that's because the way we've designed things forever is that you don't assume every employee that you hire is perfect, right? Everybody makes mistakes. So the human processes that we've been defining for forever are robust to one person failing. And therefore, if you're not trying to replace the whole thing, right? If you don't want it to solve everything in the world, but you have targeted things that it can solve that a person could have done or something else, it works very, very well. So I think as long as you actually understand what it does and don't think that it can solve, every problem, then you don't run into these problems, right? We design and deploy, NEC is deploying a huge number of large language models and AI systems, and they're all based around this idea of, either make sure that there's a verification or make sure you're using it in a situation where the results are extending human knowledge rather than replacing or making a decision, right?
Well, one last comment. Yeah.
Okay. I think we're just going to use it. What's going to happen is if someone is doing your job 10% better using AI that they don't check the safety for, your company goes under, their company doesn't. And it's so competitive. At some point, I think we'll just jump on it. You see that you're talking about the AI for cars. We're using it, even though, it's not that safe. It's just on the streets. It can kill people, and there's some cases that it did. We're doing it because it's competition. Oh, what if the Chinese figure it out before us? I'm going to make a missile. Well, if the Russian missile is better than my AI, so I have to build mine. So I think the competition is so cutthroat. We'll just go for it. We're just going for it. Look at what's going on. There's millions of cars on the street. They're just going, and maybe they put a bug in yours, and in the middle of your drive, it's going to just turn to the left and kill you. You're still using it. There's no saying that it won't. I know, but I'm just saying, the point is we're just doing it.
I guess there are challenges on the law systems and everything, like who is responsible for what if that happens. We just have to keep everything going together with AI. So with this, we are running out of time, so we thank the speakers again for having a wonderful session.